In statistical mechanics, the Potts model, a generalization of the Ising model, is a model of interacting spins on a crystalline lattice. By studying the Potts model, one may gain insight into the behavior of ferromagnets and certain other phenomena of solid-state physics. The strength of the Potts model is not so much that it models these physical systems well. It is rather that the one-dimensional case is exactly solvable, and that it has a rich mathematical formulation that has been studied extensively. The model is named after Renfrey Potts, who described the model near the end of his 1951 Ph.D. thesis. The model was related to the planar Potts, or clock model, which was suggested to him by his advisor, Cyril Domb. The four-state planar Potts model is sometimes known as the Ashkin-Teller model, after Julius Ashkin and Edward Teller, who considered an equivalent model in 1943. The Potts model is related to, and generalized by, several other models, including the X-phi model, the Heisenberg model and the n-vector model. The infinite-range Potts model is known as the KAC model, when the spins are taken to interact in a non-abelian manner. The model is related to the flux tube model, which is used to discuss confinement in quantum chromodynamics. Generalizations of the Potts model have also been used to model grain growth in metals and coarsening in foams. A further generalization of these methods by James Glazier and François Graner, known as the cellular Potts model, has been used to simulate static and kinetic phenomena in foam and biological morphogenesis. Physical description. The Potts model consists of spins that are placed on a lattice. The lattice is usually taken to be a two-dimensional rectangular Euclidean lattice, but is often generalized to other dimensions or other lattices. Domb originally suggested that the spin take one of q possible values, distributed uniformly about the circle, at angles theta n equals 2 pi n q. Display style theta underscore n equals frac 2 pi n q. Closing curly bracket, where n equals 1 q, and that the interaction Hamiltonian be given by h c equals j c I j cos theta s I minus theta s j. Display style h underscore c equals j underscore c sum underscore I j cos left theta underscore s underscore I theta underscore s underscore j right. Closing curly bracket, with a sum running over the nearest neighbor pairs I j over all lattice sites. The site colors C take on values in 1 q. Here, Jc is a coupling constant, determining the interaction strength. This model is now known as the vector Potts model or the clock model. Potts provided the location in 2 dimensions of the phase transition, for q equals 3 and 4, in the limit as q infinity. This becomes the X-phi model. What is now known as the standard Potts model was suggested by Potts in the course of his study above, and uses a simpler Hamiltonian, given by h p equals minus j p I j delta s I s j. Display style h underscore p equals j underscore p sum underscore I j delta s underscore I s underscore j backslash closing curly bracket, where delta c sj is the Kronecker delta, which equals 1 whenever c equals sj and 0 otherwise. The q equals 2 standard Potts model is equivalent to the Ising model and the two-state vector Potts model, with jp equals minus 2 jc. The q equals 3 standard Potts model is equivalent to the three-state vector Potts model, with Jp equals minus 3/2 Jc. A common generalization is to introduce an external magnetic field term H, and moving the parameters inside the sums and allowing them to vary across the model. Beta H G equals minus beta I J J I J delta S I S J minus I H I S I. Display style beta H underscore G equals beta sum underscore I J J underscore I J delta S underscore I S underscore J sum underscore I H underscore I S underscore I. Closing curly bracket, where beta equals 1, kt the inverse temperature, k the Boltzmann constant and T the temperature. The summation may run over more distant neighbors on the lattice, or may in fact be an infinite range force. Different papers may adopt slightly different conventions, which can alter H and the associated partition function by additive or multiplicative constants. Discussion. Despite its simplicity as a model of a physical system, the Potts model is useful as a model system for the study of phase transitions. For example, two-dimensional lattices with J greater than 0 exhibit a first-order transition if Q greater than 4. When Q4, a continuous transition is observed, as in the Ising model where QE equals 2. Further use is found through the model's relation to percolation problems and the Tut and chromatic polynomials found in combinatorics. The model has a close relation to the Fortuyn-Castellan random cluster model, another model in statistical mechanics. Understanding this relationship has helped develop efficient Markov chain Monte Carlo methods for numerical exploration of the model at small q. For integer values of Q3, the model displays the phenomenon of interfacial adsorption, with intriguing critical wetting properties when fixing opposite boundaries in two different states. Measure theoretic description. The one-dimensional Potts model may be expressed in terms of a subshift of finite type, and thus gains access to all of the mathematical techniques associated with this formalism. In particular, it can be solved exactly using the techniques of transfer operators. However, Ernst Ising used combinatorial methods to solve the Ising model, which is the ancestor of the Potts model. In his 1924 Ph.D. thesis, this section develops the mathematical formalism, based on measure theory, behind this solution, while the example below is developed for the one-dimensional case. Many of the arguments, and almost all of the notation, generalizes easily to any number of dimensions. Some of the formalism is also broad enough to handle related models, such as the X-phi model, the Heisenberg model and the n-vector model. Topology of the space of states. Let Q equals 1. Q be a finite set of symbols, and let Q, Z, equals, opening curly bracket, S, equals, S, minus 1, S, 0, S, 1, S, K, Q, K, Z, closing curly bracket, display style Q caret math BF Z equals S equals L dots, S underscore minus 1, S underscore 0, S underscore 1, L dots, S underscore K in Q, for all K in math BF Z. Be the set of all bi-infinite strings of values from the set Q. This set is called a full shift. For defining the Potts model, either this whole space, or a certain subset of it, a subshift of finite type, may be used. Shifts get this name because there exists a natural operator on this space, the shift operator tau, QZ, acting as tau S K equals S K plus 1. Display style tau S underscore K equals S underscore K plus 1. This set has a natural product topology. The base for this topology are the cylinder sets C M Xi 0 Xi K equals opening curly bracket S Q Z S M equals Xi 0 S M plus K equals Xi K closing curly bracket. Display style C underscore M Xi underscore 0 L dots Xi underscore K equals S in Q caret math BF Z S underscore M equals Xi underscore 0 L dots S underscore M plus K equals Xi underscore K. That is the set of all possible strings where K plus 1 spins match up exactly to a given specific set of values Xi 0, Xi K. Explicit representations for the cylinder sets can be gotten by noting that the string of values corresponds to a q-adic number, and thus, intuitively, the product topology resembles that of the real number line. Interaction energy. The interaction between the spins is then given by a continuous function v. QZR on this topology. Any continuous function will do. For example, v s equals minus j delta s 0 s 1. Display style v s equals j delta s underscore 0 s underscore 1. Closing curly bracket will be seen to describe the interaction between nearest neighbors. Of course, different functions give different interactions. So a function of S0, S1 and S2 will describe a next nearest neighbor interaction. A function V gives interaction energy between a set of spins. It is not the Hamiltonian, but is used to build it. The argument to the function V is an element SQZ, that is, an infinite string of spins. In the above example, the function V just picked out two spins out of the infinite string. The values S0 and S1. In general, the function V may depend on some or all of the spins. Currently, only those that depend on a finite number are exactly solvable. Define the function Hn, QZR as Hn, S equals K equals 0, N, V, tau, K, S. Display style H underscore N. S equals sum underscore K equals 0 caret N V tau caret K S closing curly bracket. This function can be seen to consist of two parts: the self-energy of a configuration S0, S1, Sn of spins, plus the interaction energy of this set and all the other spins in the lattice. The n-infinity limit of this function is the Hamiltonian of the system. For finite n, these are sometimes called the finite state Hamiltonians. Partition function and measure. The corresponding finite state partition function is given by Z, n, v, equals S, 0, S, n, q, exp, minus, beta, h, n, c, 0, s, 0, s, 1, s, n, display style z underscore n, v, equals sum underscore s underscore 0, l dots, s underscore n, in q, exp, beta h underscore n, c underscore 0, s underscore 0, s underscore 1, l dots, s underscore n, closing curly bracket, with CO being the cylinder sets defined above. Here, beta equals 1, kt, where K is Boltzmann's constant, and T is the temperature. It is very common in mathematical treatments to set beta equals 1, as it is easily regained by rescaling the interaction energy. This partition function is written as a function of the interaction V to emphasize that it is only a function of the interaction, and not of any specific configuration of spins. The partition function, together with the Hamiltonian, are used to define a measure on the Borel sigma algebra in the following way. The measure of a cylinder set, i.e., an element of the base, is given by mu c k s 0 s 1 s n equals 1 z n v exp minus beta h n c k s 0 s 1 s n. Display style mu c underscore k s underscore 0 s underscore 1 l dots s underscore n equals frac 1 z underscore n v exp beta h underscore n c underscore k s underscore 0 s underscore 1 l dots s underscore n. Closing curly bracket. One can then extend bi-countable additivity to the full sigma algebra. This measure is a probability measure. It gives the likelihood of a given configuration occurring in the configuration space QZ. By endowing the configuration space with a probability measure built from a Hamiltonian in this way, the configuration space turns into a canonical ensemble. Most thermodynamic properties can be expressed directly in terms of the partition function. Thus, for example, the Helmholtz free energy is given by A n v equals minus k t log z n v. Display style A underscore n v equals kt log z underscore n v. Closing curly bracket. Another important related quantity is the topological pressure, defined as P v equals lim n infinity 1 n log z n v. Display style P v equals lim underscore n 2 infinity frac 1 n log z underscore n v. Closing curly bracket, which will show up as the logarithm of the leading eigenvalue of the transfer operator of the solution. Free field solution. The simplest model is the model where there is no interaction at all, and so V equals C and Hn equals C, with C constant and independent of any spin configuration. The partition function becomes Z n C equals E minus C beta S 0 S n Q 1. Display style Z underscore n C equals E caret C beta sum underscore S underscore 0 L dots S underscore n in Q1. If all states are allowed, that is, the underlying set of states is given by a full shift, then the sum may be trivially evaluated as Z n C equals E minus C beta Q n plus 1. Display style Z underscore n C equals E caret C beta Q caret n plus 1. If neighboring spins are only allowed in certain specific configurations, then the state space is given by a subshift of finite type. The partition function may then be written as Z n C equals E minus C beta pipe fix tau n pipe equals E minus C beta tr a n. Display style Z underscore n C equals E caret C beta M box fix tau caret n equals e caret c beta m box tr a caret n, where card is the cardinality account of a set, and fix is the set of fixed points of the iterated shift function. Fix tau n equals opening curly bracket s q z tau n s equals s closing curly bracket display style m box fix tau caret n equals s in q caret math bf z tau caret n s equals s. The Q times Q matrix A is the adjacency matrix specifying which neighboring spin values are allowed. Interacting model. The simplest case of the interacting model is the Ising model, where the spin can only take on one of two values, Sn minus 1, 1, and only nearest neighbor spins interact. The interaction potential is given by V sigma equals minus j p s 0 s 1 display style V sigma equals j underscore p s underscore 0 s underscore 1 closing curly bracket. This potential can be captured in a 2 times 2 matrix with matrix elements m sigma single quote equals exp beta j p sigma single quote display style m underscore sigma equals exp left beta j underscore p sigma right closing curly bracket with the index sigma minus 1 1. The partition function is then given by z n v equals tr m n display style z underscore n v equals m box tr m caret n. The general solution for an arbitrary number of spins and an arbitrary finite range interaction is given by the same general form. In this case, the precise expression for the matrix M is a bit more complex. The goal of solving a model such as the Potts model is to give an exact closed-form expression for the partition function and an expression for the Gibbs states or equilibrium states in the limit of n infinity, the thermodynamic limit. The Potts model in signal and image processing. The Potts model has applications in signal reconstruction. Assume that we are given noisy observation of a piecewise constant signal g in Rn. To recover g from the noisy observation vector f in Rn, one seeks a minimizer of the corresponding inverse problem, the LP Potts functional p gamma u, which is defined by p gamma u equals gamma u 0 plus u minus f p equals gamma hash opening curly bracket I u I does not equal u I plus 1 closing curly bracket plus I equals 1 n pipe u I minus f I pipe p display style p underscore gamma u equals gamma nabla u underscore 0 plus uf underscore p caret p equals gamma hash I u underscore I neq u underscore I plus 1 plus sum underscore I equals 1 caret n u underscore I f underscore I caret p. The jump penalty u 0 display style nabla u underscore 0 forces piecewise constant solutions in the data term u minus f p display style uf underscore p caret p couples the minimizing candidate u to the data f. The parameter gamma greater than 0 controls the trade-off between regularity and data fidelity. There are fast algorithms for the exact minimization of the L1 and the L2 Potts functional Friedrich, Kemp, Liebscher, Winkler, 2008. In image processing, the Potts functional is related to the segmentation problem. However, in 2 dimensions the problem is NP-hard. Boykov, Wechsler, Zabi, 2001. See also, square lattice Ising model, minimal models. Ashkin, Julius, Teller, Edward, 1943. Statistics of 2-dimensional lattices with 4 components. Phys. Rev. 64. 5-6. 178-184. Bibcode. 1943 PHRV. 64. 178A. DOI. 10.1103. Phys. Rev. 64.178. Grana, François. Glazier, James A. 1992. Simulation of biological cell sorting using a 2-dimensional extended Potts model. Phys. Rev. Let. 69. 13. 2013-2016. Bibcode. 1992 PHRVL. 69.2013G. DOI. 10.1103. Phys. Revlet. 69.2013. Potts. Renfrey B. 1952. Some generalized order disorder transformations. Mathematical proceedings. 48. 1. 106-109. Bibcode. 1952 PCPS. 48. 106p. DOI. 10.1017, SO3050041000274419. Wu, FAU. 1982. The Potts model. Rev. Mod. Phys. 54. 1. 235-268. Bibcode. 1982 RVMP. 54. 235W. DOI. 10.1103. Rev. Mod. Phys. 54.235. Friedrich, F. Kemp, A. Liebscher, V. Winkler, G. 2008. Complexity Penalized M Estimation. Fast Computation. Journal of Computational and Graphical Statistics. 17. 1. 201-224. Mr. 2,424,802. DOI. 10.1198 106,186,008x285591. Boykov, Y. A. Al. 2001. Fast Approximate Energy Minimization via Graph Cuts. Pattern Analysis and Machine Intelligence. IEEE Transactions on 1222-1239. Selke, Walter, Hughes, David A. 1983. Interfacial Adsorption in Planar Potts Models. Zeitschrift für Physik B. 50. 2. 113-116. Bibcode. 1983 ZPHYB. 50. 113S. DOI. 10.1007 BFO13040993. Haggard, Gary. Pierce, David J. Royal, Gordon. Code for Efficiently Computing TUT. Chromatic and Flow Polynomials.